Hey Calc peeps, welcome to 3.9 related rates. Related rates are applications of implicit differentiation. So just a reminder, how would we find dr dt for r squared plus 2r t squared plus sine of r? Well, remember, focus on the numerator variable. Anytime we take the derivative of an r term, we're going to tag on dr dt. So the derivative of r squared is 2r, then tag on the dr dt. Plus, now we have to use the product rule here because that's 2r times t squared. So the derivative of 2r is 2, but I just took the derivative of an r term, so I have to tag on the dr dt times the plain old second plus the plain old first. Now I'm taking the derivative of t squared, so that's 2t, but because that's not the numerator variable, I don't have to tag on a dr dt. And then I have the sine of r, which is the cosine of r, dr dt, right? And then we would solve for dr dt. So I would get dr dt is equal to, I'm going to say negative, I didn't do this one out yet because I forgot to do that one, but I'm going to say it's going to be negative 4rt. Let me know if you get something different. 4rt, because that's going to come over here. That one's going to come over there. And then I'm going to get 2r plus 2t squared from that term, and I'm going to get minus the cosine of r. Okay? So that's how we did implicit differentiation. So today we're going to talk about related rates, and related rates are applications or word problems that involve implicit differentiation. So here's your guidelines right here. If possible, draw a picture. Always identify the quantity you're looking for. Keep in mind what information you have. And then we're going to have d variable dt. So typically with related rate problems where things are changing with respect to time, and we can often be identified in the problem by using the words increasing, decreasing, changing. If the rate is decreasing, make sure you make the quantity negative. Identify an equation that relates all your variables. Take the derivative of each side with respect to t. Don't plug anything in anything in that's changing. Do not plug in until after you set up the equation and took the derivative. And then go back to equation 4 to find anything we're looking for, and then solve for the desired quantity. I know that's a lot of information without actually seeing a problem. So let's take a look at our first problem. All right. When a circular shield of bronze is heated over a fire, its radius increases, so metal increases as it heats, and its radius is increasing at a rate of 15 centimeters per second. So as its radius is increasing, its area is also increasing. And I want to know what is the rate of change of area at a snapshot in time. So I have my circular shield and it's getting heated over fire, right? And this guy is increasing. So I have my circular shield, I see area and I see radius. Right, so this is my radius of my circular shield. Now my radius is changing, thus the area is changing. And as the radius changes, the circular shield is getting bigger and bigger. I'm going to take a picture right here when the radius is 50 centimeters is what I want to know how the area is changing. We're going to worry about that afterwards. So our problem is our variable. We're going to use, I suggest using letters that remind yourself of the variable of interest instead of using x's and y's all the time, because then you don't have to remember which was x and which was y. Clearly a is area and radius is r. So the equation that relates these variables, how do we relate the area and the radius? Well, you should know the relationship between area and radius. The area is the constant pi times r squared. Now as time goes on, the radius is changing, right? And we know how the radius is changing. The rate of change of the radius is the radius increases at a rate. So this is telling me right here that this is the derivative. The derivative is the rate of change. Increases at a rate of, now notice we have centimeters over second. Radius is centimeters, times is in seconds. So 15 centimeters per second. What we're looking for is how is the area changing? Changing is the derivative, rate of change, dA dt. All right, so now keep in mind, we know that A is equal to pi r squared. Now we're going to take the derivative of both sides with respect to t. So we're going to take the derivative of A with respect to t, and we're going to take the derivative of r with respect to t. So dr and dr dt, dA dt, we're going to always tag on these differentials. So now as long as we're not taking the derivative of a t, we have to tag on that dr dt or the dA dt. So the derivative of a is 1, and then you tag on d variable dt. Now remember, pi is just a constant, so this is really no different than taking the derivative of like 8r squared or 5r squared. We're going to bring the power out front. Leave the power, leave the variable alone, drop the power by 1, and now we tag on d variable dt. So we know that a equals pi r squared. So the rate of change of the area, I'm going to rewrite this, the rate of change of the area, this is the relationship between the radius and the rate of change of the area. Now we go back and plug in what we know and think about what we're looking for. This is what we're looking for. So from the information given, we should be able to plug in everything else. We know we're looking at a snapshot in time when the radius is 50. And we know that it's changing at a rate of 15. Now when I plug things in, I don't put the units in until the very end. It just gets a little bit messy. So what we have here is dA dt equals 2 pi times 50 times 15. Which is equal to, leave it in terms of pi, I'm going to say 1500 pi, unless otherwise stated. Now we have to put our units in. Well, area, well, we were talking about everything is in terms of centimeters, so area is centimeters squared, so that's my numerator unit, centimeters squared, and time was in terms of seconds. So as the shield increases, when the radius hits 50 centimeters, the area is increasing at 1500 pi centimeters square per second. Let's set up a couple more. A spherical snowball. Well, snow melts, right? And the volume of the snowball is decreasing at a rate of 2 centimeters cubed per minute. How fast is the radius changing when the diameter is 10? So here you need to know the volume of a sphere. If you're not sure what the volume of a sphere is, well, you can always look it up. But you should know anything, pretty much anything square and anything round, right? So we have an orange snowball here, right? And here's the radius of my snowball. So we know the volume decreases at a rate of 2 centimeters per minute, centimeters cubed per minute. So we know dV dt, the rate of change of the volume, is 2 centimeters cubed per minute. Right? How fast is the radius changing? Looking for, the volume is decreasing at a rate of 2 centimeters per minute. So I made a mistake that I said earlier, not to forget to include, if something's decreasing, then its rate of change is negative. Right? We're looking for how fast the radius is changing. So changing is just derivatives, rates of change. So we have our volume, which I'll call V, my radius, which I'll call R, and the relationship between the volume and the radius in the sphere is 4/3 pi r cubed. 4/3 and pi are constants. So now we're going to take the derivative of both sides with respect to t. The derivative of v is 1. Then tag on d variable dt. Bring the 3 out front. So we get 4 pi r squared. Because the 3, when we bring the 3 out front, it cancels with the 3 in the denominator. And then we're going to tag on d variable dt. All right, this is what we're looking for, right? We know that the volume is -2. All right, what's the radius though? How fast is the radius changing when the diameter of the snowball is 10? So always from the information given, you'll be able to fill in everything here. Well, the diameter is 10. So what's the radius that we need for our template? Well, the radius is half of the diameter, so that's going to become 5. So we get -2 equals 4 pi 5 squared times dr dt. Right, we solve for dr dt. And the radius, as expected, is going to be negative, and it's -1 over 50 pi. Radius is in centimeters, and my time unit is minutes. So at this point, this snapshot in time, when the diameter of the snowball is 10 centimeters, the radius is decreasing at a rate of -1 over 50 pi centimeters per minute. All right, no related rate section would be complete without a sliding ladder problem. So let's take a look at problem number 3. We have a ladder leaning against a wall, and the ladder sliding away from the building horizontally. What I want to know is how fast is the ladder sliding down the house? So I have my building, I have my ground, and we always assume we're in a perfect scenario. Everything's nice and square, so here's my ladder, all right? So a ladder 20 feet long. So now the ladder is 20 feet long. Notice this length between my fingers, the green line, the length of the ladder, doesn't change. It's always going to be 20. Even as the ladder moves, as the base goes down, the top's going to slide down, but the length of the ladder is not going to change. So I can assign it the value of 20. The bottom of the ladder slides away from the building horizontally. So this distance is changing right here. The base of the ladder. So we're going to call that something. I'm going to call it B for the base of the ladder. And that's changing. So I'm going to assign it a variable. And then we want to know how fast the ladder is sliding down the house. So I'm going to call that H. Now, even though we want to know when the top of the ladder is 8 feet from the ground, what happens when that is 8, I'm not putting 8 there because that's just a snapshot in time. This length is changing. So I'm just going to call it H. So what we have here is we have a right triangle, assuming that the building is makes a right angle with the ground, in which we can always assume that's the case unless otherwise stated. So I'm not sure if you immediately see a relationship between these variables, but h squared plus b squared equals 20 squared. So in other words, h squared plus b squared equals 400. Right now, so we're looking for, we know the bottom of the ladder slides away horizontally, so we know that dB dt is equal to 4 feet per second. And if the bottom of the ladder is sliding away from the building, then B is getting bigger, so it's positive 4 feet per second. What we're looking for is how the rate of change at which it's sliding down the house. So now once we have our equation set up, I can take the derivative. The derivative of h squared is 2h, and then tag on d variable dt, plus 2b d variable dt, and the derivative of 400 is 0. All right, so now we got to plug in everything we know and decide what we're looking for. So this is what we're looking for. Okay. So we know that this is h is 8 because it's telling me when the ladder is 8 from the ground. So we're taking that snapshot in time as things are changing. We're told that this is 4. All right, so the question is, what is b? Well, let's think about this. If we look at our snapshot in time, okay, we're looking at when this is 8, this is always 20. What is this going to be? So as the triangle is getting shorter but longer, things are changing, but we're looking at this very instant in time. So we're going to use Pythagorean's theorem. And Pythagorean's theorem tells us that 8 squared plus whatever the length of that base is squared is equal to 20 squared. So 400 minus 64, right? So we get this squared is equal to 336. So the length of that base at this instant in time is the square root of 336. So that's what's going to go here, square root of 336. So we have 2 times 8 times what we're looking for, dh dt, is equal to 2 square root of 336 times 4. Whoops, sorry, that should be plus. That equals 0. Right, now let's solve for dh dt. So dh dt, I'm going to subtract this from both sides. So we get negative 8 square root of 336 all over, and then I'm going to divide out the 16. So this is equal to negative 8. Oh, no, let's do 336. There we go. All over 2. Now my guess is your online homework will accept this as an answer, but the square root of 336 can also be written as 4 square root of 21 all over 2. So really the nice simplified exact answer is -2 square root of 21. And my units are height and time, so feet per second. And if it asks for an approximate answer, just follow the direction. So it's sliding down at about a rate of 9.2 feet per second. All right, I got 2 more problems for you. Sometimes the problems are a little ambiguous, so hopefully you don't come across this. Usually I try to make it clear what exactly we are looking for. In this case, we have 2 students are walking on straight roads that meet at a right angle right here. So here's my right angle, here are my straight roads. Student A is approaching the intersection at 2 meters per second, and student B is moving away from the intersection at 1 meter per second. And it says, at what rate is the angle changing when A is 10 and B is 20? So this is not very clear what angle it is. So we can pick an angle, and in fact, they're going to come out to be the same answer. They're just going to be opposite in sign. So for simplicity, let's look at this angle up here. So I'm going to be interested in this angle. So A is changing, the length of this line is changing as the student walks, this is becoming smaller, and as this student walks away, that line is becoming longer. And I know the rate at which student A is walking. Student A is walking at a rate of 2 meters per second, and it's negative because that line is getting smaller as the student walks closer to the intersection. And we know that dB dt is 1, and it's positive because as the student walks away from the intersection, right? So now what we look for here, yes, this is a right triangle, but I would not introduce Pythagorean's theorem. What I would do is what we're looking for is a relationship between A, B, and theta. So instead of introducing another part to the problem that's not necessary, why don't we just find a relationship between theta inside a right triangle, the opposite side, and the adjacent side. So hopefully that triggered for you that the tangent of theta is equal to A over B. Right, so now we're working with 3 variables. Theta is changing, A is changing, and B is changing. So notice I didn't stick anything in yet until I take derivatives. Now here, you can take the derivative of the tangent, which is the secant squared, and then we would have to use the quotient rule here. All right, so, or we could bring the B over to the other side and use the product rule. I'm gonna do that because I'd much rather use the product rule. Isn't it true that B tangent of theta equals A? Then that way we don't have to work with fractions. Now we're going to take the derivative of both sides, keeping in mind that we have B times the tangent of theta, so we have to use the product rule. The derivative of B is 1, and then you tag on d variable dt times the second. So the derivative of B is 1 dB dt times the plain old tangent plus the plain old B times the derivative of the tangent, which is the secant squared of theta, and then we have to tag on d variable dt. And that equals the derivative of A is 1, and then we tag on d variable dt. All right, so lots of stuff going on here. Let's see, what do we know and what are we looking for? Well, we know the rate of change of B is 1. We know the rate of change of A is -2. And then it says student A approaches the intersections. Let's go back and see what else we know. Student A approaches the intersection at 2 meters per second. We got that here. Student B moves away at 1 meter per second. At what rate is the angle changing? So this is what we are looking for. When A is 10 meters from the intersection, so we don't even have A in there anymore, so it doesn't matter for right this moment. And B is 20, so we have to put 20 in right here. Right. So, but now from the information given, this is what we're solving for. This is the unknown. We need to find the secant and the tangent of the angle. Now remember, we have a snapshot in time here. So when we look at our snapshot, right at this instant of interest, we know here this A 10 is now important and B is 20. And here is the angle. Now, I don't ever care what the angle is, but I do need to know what both the tangent of the angle is and the secant of the angle. Looking at this picture, the tangent of the angle is the opposite over the adjacent. So this is 10 over 20, or you could just call that 10 halves. But I need to know the secant of the angle to put it in there. Well, in order to know the secant, I need to know the hypotenuse of this triangle. So using Pythagorean's theorem, right, the hypotenuse of this triangle is Well, the hypotenuse squared is 20 squared plus 10 squared. So the hypotenuse is going to be the square root of 500, right? So the secant of this angle, so I'm going to call this the square root of 500. So now we need to know the secant of the angle. The secant of the angle. Well, the secant of the angle, well, I think of it in terms of cosine. Cosine is the adjacent over the hypotenuse. So the secant is the hypotenuse over the adjacent. So the square root of 500 all over 20. So therefore, the secant squared of the angle is the square root of 500 all over 20 squared, which is 5/4. So this is just going to become 5/4. Right, so now let's clean this all up. We have 1 times 10 over 20 plus 20 times 5/4 times d theta dt equals 1 times -2. Okay, and now we're going to solve for d theta dt. So I'm cleaning this up. This is just 1/2 plus 25 d theta dt equals -2. Subtract 1/2, we get 25 d theta dt equals -2. Oh, -5/2, because I forgot to subtract 1/2. And then I'm now going to do d theta dt equals -5/2 times 1 over 25, which is -1/10. My angle is in radians. My time is in seconds. So as this person moves at a rate 2 meters per second towards the intersection, that student moves away at 1 meter per second. The angle is decreasing at a rate of 1/10 radian per second. All right, guys, one more problem. Hang in there. I love these problems because they seem, this next one, it seems complicated, but it's really not. So that's what I'm trying to say, a little bit difficultly. All right, so we have a light on the ground. So here's my light. It's 20 meters from the building. So the distance between the light and the building is not changing. So I can assign that the value 20. A man 2 meters tall walks from the light directly towards the building. So we have some guy in here, right? And he's walking this way, right? And I know that he is 2 meters tall. So I can put that in there. He walks from the light toward the building at a rate of 1 meter per second. It says, how fast is the length of his shadow on the building changing when he's 14 meters from the building? All right, so let's do this. I'm gonna do, the guy is walking. There's my light. This is going to be the length of his shadow right here. That's going to be the length of his shadow because as the light shines from behind him, it's going to make a reflection, and this is going to be the length of his shadow. So we're going to call that S. And as the man moves, that shadow, if he moves towards the building, that shadow is going to get smaller. As he moves away from the building, that shadow is going to get longer. All right, so now let me see. He walks from the light directly towards the building at a rate of 1 meter per second. So there's 2 ways we can go about this. We can look at this right here, and we can look at this right here. Now, both of these distances are changing, but there is a relationship. Right? I'm going to call this, he's walking, so I'm going to call that W. And do you agree that W is changing? As he moves towards the building, W is changing. So what is W? Well, what do we know? It says a light is 20 meters from the building, a man 2 meters tall. We have that there. And it says a man walks from the light directly towards the building at a rate of 1 meter per second. So we know that dW dt is changing at a rate of 1 meter per second. Now be careful here, because if he's walking towards the building, do you agree that W is getting smaller? So we have to say that dWTD is -1 meter per second. It says, how fast is the length of his shadow on the building changing? So looking for the rate of change of his shadow, right? So when he is 14 meters from the building, so when W is 14, right? But we need to have, before we stick in W equals 14 or anything, we have to have a relationship between W and S. How can we relate W and S here? So again, this might look a little tricky, but it's really not that bad. This is pretty cool. So if this distance is 20 and his distance to the building is W, then this distance here is 20 minus W. If he is 15 feet from the building, then he is 5 feet away from the light. If he is 18 feet from the building, then he'd be 2 feet away from the light. Now, why does that mean something? Well, the trick here is to notice that we have similar triangles. We have this big triangle right here, right? And then we also have this little triangle right here. And what's cool about similar triangles is the ratios of their sides are equivalent. So what I'm going to do is look at this big yellow triangle, and I'm going to look at if I refer to this angle under my right finger right here, and the tangent of this angle is going to be S over 20. So S over 20 is equivalent to, well, if I look at just the little triangle, this angle is still the same angle, and its tangent is now going to be 2 over 20 minus W. So we're just going to use similar triangles and create this little itty bitty tiny relationship. S over 20 is equal to 2 over 20 minus W. And that's going to be how we're going to solve this problem. So this is our relationship. You can use the quotient rule if you want. I prefer to multiply and use the product rule. So I'm going to multiply both sides by 20 and 20 minus W, or just cross multiply. I get 20S minus SW is equal to 40. Now that I have everything here, I'm going to take the derivatives. The derivative of 20S is 20 ds dt minus, well, be careful here because I have to take the derivative of a product. The derivative of S is 1 ds dt. So that's the derivative of the first times the second plus the first times the derivative of W, which is 1 dw dt. And that equals the derivative of 40, which is 0. All right, so now let's plug in everything that we know. How fast is the length of his shadow on the building changing? So this is what's the unknown, right? When he is 14 meters from the building. So when W is 14. Well, when W is 14, we need to now know what S is. But I'm sure from the information given, if we look at that snapshot in time, right, we can determine S. So we're going to do, let's see, we don't know what S is, but we do know that this is 14, this is 6, right? And this is 2. We need to know what S is. So how can we determine what S is? Well, let's go back to, I'm going to go back to S over 20 is equal to 2 over 20 minus W, right? W is 14, so S over 20 is equal to 2 over 6. So S is equal to 40 over 6, or 20 over 3. So that's going to be 20 over 3. And let's plug it all in. Let's see what we have. We have 20 ds dt minus ds dt. Whoops, got it, okay. Times 14 minus 20 over 3. Now we know dw dt, so I forgot to write that on here. He's walking at a rate of 1 meter per second, so we know that that's -1. So 20 over 3 times -1, and that equals 0. Now I'm going to challenge you to solve for ds dt, so to do the work in between. And you should get -10 over 9 meters per second. All right, so now the trick here is that every problem is different, and the only way you get good at these is by trying lots of different types of problems. So not only do your homework on your online program, but make sure you're looking at those problems assigned in the textbook too. All right, have fun. See you soon.